Good morning, everyone. My name is Lezina from the Intelligent Space Robotics Laboratory at Scopus Institute of Science and Technology. Today I will present GraspSense, a pipeline for a physically grounded grasp and grip planning for a dexterous robotic hand, driven by a language command and a map of admissible contact forces. This is a joint work with Yelizaveta Semenyakina and Ivan Snegirev. Let me start with a simple observation. Take a paper cup. A modern grasp planner will give you so many valid ways to pick it up: stable, reachable, collision-free. You can execute one of them perfectly and still crush the cup. The reason is that essentially all grasp planner treats the object surface as mechanical uniform. It is not. On this cup, the rim is rolled reinforced edge. The wall right next to it is a single thin sheet of paper. In our measurements, those two regions differ by almost an order of magnitude in the force they can take. So geometry tells you where the hand can close. It doesn't tell you where the object can be touched or how hard. If the fingers land on the weak region, a geometrically perfect grasp still damages the object. The gap between geometric feasibility and mechanical admissibility is what this work addresses. We built on 4 lines of work: dexterous grasp generation and ranking. DexGraspNet gives large-scale candidate generation for multi-fingered hands, and methods like Grace rank those candidates by stability, kinematics, and task relevance. We add local force admissibility as an additional ranking criterion. Force-aware and compliant manipulation. Impedance control gives physically consistent force regulation. FEM-based framework give high-fidelity structure analysis. Our contribution is to grow the impedance set point in object-specific bounds instead of generic compliant parameters. Language-guided manipulation. LLMs are already used for high-level task planning and semantic grasping. We use Quen to parse the operator command into object, action, and interaction mode. Perception and reconstruction. YOLO word, SUM, and SUM3D gives us an object central 3D model, which we convert to USD for Isaac Sim. What is missing across all 4 is a single system that connects the object, especially non-uniform structure, to both grasp selection and grip force. That is the gap we close. The central object in this work is a force map, a pure surface bound on a mechanically safe contact force. For every point on the reconstructed model, it gives the maximum lateral force that can be applied without irreversible deformation. On that left, you can see it on a paper cup. Blue is a high admissible load, red is low. In B, a grasp chosen by a geometric feasibility alone. The context land on the thin wall and force-bound validation become possible. In C, the same object with force map-aware re-ranking contacts a directed to the mechanically admissible rim and mid-body zone. And this is the second half of the idea. Peer finger stiffness is scaled to the locally admissible force at each contact. So the map is used twice: one to decide where to grasp, and once to decide how hard each finger holds. This gives 4 contributions. 1. Force map construction, a physics-informed bound on a safe contact force for every surface region. 2. Force map aware re-ranking, picking the mechanically safest grasp among geometric equals. 3. Impedance-based grip execution, peer finger stiffness scaled to the local admissible force. 4. The full pipeline in Isaac Sim, for a natural language command to grip execution on paper, plastic, and glass objects. The common thread, the force map, becomes a first-class element of both grasp selection and grip execution. Here is a whole system, 5 stages. The operator types or speak a command, take a paper cup carefully. Quen parse it. In parallel, an RGB image go through YOLO word and SAM. Then 3D reconstruct the object. The mesh becomes a USD asset in Isaac Sim. On that asset, we compute the force map. DexGraspNet then sample grasp candidates, which are filtered for physical feasibility and for task call consistency, and re-ranked used for the map. The selected grasp is reached by a diffusion-based motion planner, and the grip itself is executed by impedance control, whose stiffness comes from the map. Let me walk through the stages that matter most. The command is parsed by Quen 2.5 in inference mode, without task-specific fine-tuning. It produces a tuple, target object, action type pick up, pick and place, or hand over, and interaction mode. Words like gently or firmly map to a normalized force scaling factor lambda between 0 and 1, and that number survives all the way down to the fingertips at execution time. The object identity is used twice. YOLOWord takes it as an open vocabulary text query to localize the object, and the structural analysis use it to condition the material model. SEM turns the detection point into a pixel-accurate mask. Some 3D reconstruct the mesh from the masked RGB image, and we import it into IXXIM as USD, with an SDF collider for accurate contact localization and material physics keyed to the object. Now the force map itself. We deliberately do not solve a full FEM problem. We want something that runs per object in line with the pipeline. Instead, we use a physics-informed geometric approximation in 4 steps. First, BCA on the mesh vertices gives a principal frame aligned with the object's main axis. Second, we uh, discretize the lateral surface in the L-high layers and A angular bins. Third, for each cell, we estimate the local wall thicknesses by 2 stages ray casting. One ray from outside give the outer surface point and its normal. A second ray along that normal give the inner wall point. The distance between them is the thicknesses. Several probing direction per cell plus smoothing along both axes gives a stable field. First, and this turned out to matter, we refine the edges. Near boundaries, the rays can meet the inner wall and the measured thicknesses collapses artificially, exactly where real cups have reinforced rims. So for boundary layers, we double the angular resolution and sample additional sublayers. That lets the algorithm distinguish a genuinely thin region from a structurally reinforced edge. The admissible force then grows with the local wall thicknesses, received a Gaussian bonus near reinforced layers, is scaled by a material coefficient, and is hard clamped by a safety saline. Finally, it is projected onto the mesh vertices and stored per vertex in the USD mode. Storing it per vertex matters. It makes the lookup instantaneous at any contact point, both during ranking and during control. And here is why a heuristic wouldn't be enough. There are out 3 objects with their force maps. For the paper cup, the rim takes 41 newtons and the wall 4.8, a factor of 9 within one object. For the plastic cup, 3.7 versus 0.3 newtons. That wall is essentially a fragile membrane. And for the glass goblet, the ordering flips completely. The safest region is not the rim, it is the stem, 565 newtons against 69 for the bowl, an 8-volt gap inside one object. So there is no rule like always grasp the rim. The safe region depends on the object and it has to be computed. Grasp selection works as following. DexGraspNet generate 50 candidates per object and filtered out physically invisible grasps. Task grasp then keeps only those consistent with the task. For the remaining candidates, we use the force map to select the best grasp. Fingertip contacts are projected onto the mesh, and the invisible force is interpreted from the triangle vertices. We score each grasp by maximizing the weakest contact force while penalizing uneven load across the fingers and select the high scoring candidate. For a delicate interaction, any grasp with the contact below the safety threshold is discarded before ranking. This is the clearest illustration of the idea. 2 grasps on the glass goblet. On the left, contacts on the bowl. The weakest contact has a budget of 69 newtons. On the right, contacts on the stem 565 newtons. Under all classical metrics, these 2 grasps differ by less than 3%. Stability, reachability, collision, all of them say the grasps are equivalent. The force map is the only criterion that tells them apart, and it rejects the one on the left. Once the grasp is chosen, a diffusion-based planner moves the hand to the pre-grasp pose, and the grip is executed by pair-finger Cartesian impedance control at 60 Hz. At each control step for every finger, we take its constant contact point, retrieve an immeasurable force by a nearest vertex query, estimate the actual normal force from the contact impulse, and select the most critical contact, the only one with the highest load ratio. The normal stiffness of the finger is the set proportional to the target force over the maximum allowed deflection, with damping co-tuned to keep a consistent transient response. The interaction mode lambda scaled on the target force. The consequence is especially non-uniform grip, soft where the object is fragile, firm where it's strong, with on one hand on one object. To experiment, the first evaluate grasp selection over baseline, maximize the classical utility score, and ignore the force map. Against it, our methods consistency move the context into the rainform zone, the rain for both cups and the steam for the goblet. The safe force budget at the weakest finger improved by factor of 8.6, 12.3, and 8.2. The safety margin admissible over applied force goes from roughly 1.2 to 2.1 up to between 5.9 and 12.4. And the baseline produced force bound violation on every object. Our selection produces none. The second experiment is laid the controller using a plastic cup with 0.3 Newton force limit. With under stiffness, the object slips. With over stiffness, it's retained, but the force limit is exceeded by 2.5 times. Our controller retained the object with zero violation and a safety margin of 1.43. Finally, changing the command from gently to default to firmly, adjust lambda from 0.3 to 1.0, narrowing the safety margin from approximately 3.3 to 1, uh, while all modes remain successful. This showed that language semantics propagate directly into the fingertip forces. To conclude, a physics-informed force map makes grasp planning physically grounded rather than purely geometric. Re-ranking on that map selects mechanically stronger regions, roughly an 8 to 12-fold improvement in the safe force budget with zero violations. Peer finger impedance keeps contact force inside the local bounds, and operator intent propagates from the command down to fingertip force. Our results are in simulation of cup-like objects, so the natural next step are deployment on the physical hand with closed-loop tactile feedback, uh, structure analysis beyond cylindrical geometries, broad statistical relation over repeated trials, and goal every sampling the biases candidate generation towards strong regions from the outset. The broad message is this: for Dexterous hand, where to grasp and how hard to hold are one problem, not two. Thank you for your attention.